Good afternoon, everyone. My name is Elijah Perrier. I'm fortunately unable to be here with you in person. However, I have been given the opportunity to present my paper on KP quantum neural networks. So without further ado, here's my presentation, and I'd love to connect with you if you're interested. Bit about me. I am a fellow at the Centre for Quantum Software and Information in Sydney, Australia. I did my PhD on quantum geometric machine learning as one of the current areas of my research focused, in particular developing analytic techniques for time-optimal quantum control problems. Today I'll be giving an introduction to KP quantum neural networks, some background on some earlier results on geometric control and KP problems, how we integrated this into quantum neural networks, the relationship between equivariant neural networks and KP quantum neural networks, and some conclusions and outlook from this research. So this talk and this paper is really about, answering this question as to whether quantum neural networks can be engineered to reproduce sub-Riemannian geodesics that define time-optimal quantum control. Now, there's a lot in there which I will unpack. So the answer is yes. So what is quantum control? Quantum control asks for time-optimal strategies to steer quantum computations to perform quantum computations in an optimal time or resource use. Quantum neural networks are a form of machine learning which can be leveraged to learn unitary transformations from data using gradient-based training. So the question is, can data-driven quantum neural networks recover what analytically has been and can be shown to be time-optimal quantum circuits in the form of sub-Riemannian geodesics? The answer is yes, and we show this via the construction of what we call a KP quantum neural network, which is an equivariant quantum neural network, which essentially integrates a Cartan geometric solution to what's called the KP problem. We show that what we call constant theta KP quantum neural networks can achieve analytic time optimality and recover geometric solutions for quantum control problems. We do this by constructing KP quantum neural networks using our constant theta handsets, which I'll explain. And fundamentally, we construct a quantum neural network whose layers respect the symmetries of the quantum control problem in question. We show that by using local optimality techniques, that the variational cost essentially implies global time optimality. What this means is that we have integrated the particular globally time optimal solutions into the layers of the neural network itself. And we give some conditions on the existence and uniqueness of KP circuits. And at the end, if I have time, I'll talk about how this solution has synergies with common problems such as lambda systems. So without further ado, I'm going to start with precisely what is the KP problem. It's a classic problem in geometric control. Certain compact Lie groups can decompose into vertical K and horizontal P subalgebras, Lie algebras, where we can use the antisymmetric subalgebra P to generate motion on the quotient or homogeneous group GK. Such groups exhibit a certain structure which allows them to be subject to what's called a Cartan decomposition. So for compact semi-simple Lie groups with a Lie algebra G and a symmetric pair GK, the Lie algebra G corresponding to the group big G, capital G, can be decomposed into a symmetric, which is K, or antisymmetric, symmetric and antisymmetric pair, KP. These two subalgebras exhibit Cartan, certain commutation relations, which are sometimes described as Cartan commutation relations, sometimes. Each of these subalgebras generates its own subgroup, capital K, capital P, and the sort of point here is that any element of the group G can be written as essentially as a decomposition via what's called the KAK decomposition, where A is a subgroup of the subgroup P. Fundamentally, GK is what's called a symmetric space, and this carries a natural sub-Riemannian geometry, which is induced by our antisymmetric generators P. Is maximally abelian. Sorry, I'm just fixing that. Sorry. Okay, right. Let's now connect this to quantum computation. So, quantum computation is naturally described as an evolution on a Lie group of unitaries. Quantum computation corresponds to unitary evolution on a Hilbert space, and for example, n cubic unitaries form a Lie group U2n or a special subgroup, SU2n. So you might have heard about qubits and multi-qubit systems. Fundamentally, when you're performing the quantum computation, that is equivalent to evolution on a unitary group, where the generators are elements of the corresponding Lie algebra. Quantum evolution needs to satisfy Schrodinger's equation. And Schrodinger's equation is written down here on the right-hand side with the quantum state psi, and the time evolution of the quantum state is generated by what's called the Hamiltonian H. The solution to Schrodinger's equation are wave functions, which are fundamentally represented here on the left, which respect unitary symmetry. They're elements of a unitary group. This is why quantum computation is fundamentally reflective of evolution across a Lie group manifold. It is very difficult to solve the time-dependent Schrodinger equation, so we approximate quantum circuits through a discretized approximation, essentially a sequence of unitary gates to reflect the quantum circuit itself. Each gate corresponds in a time-optimal sense to a geodesic segment of the manifold. The structure of quantum control, in this case, is governed by the Lie algebra of the Hamiltonians. The Hamiltonians are built from the Lie algebra of the corresponding Lie group. The Lie algebra consists of anti-Hermitian traceless matrices, and these are used to control the evolution of these systems. So what we're interested in is what are the control pulses that we can apply to the generators to generate time-optimal quantum circuits. Many quantum systems, as I said before, admit a KAK decomposition, and this is the focus of our work. So the KP problem in quantum control seeks to frame optimal quantum circuits as geodesics along this symmetric space generated by controls in P under certain energy constraints. So if we look at so this is the Schrodinger equation again. We've got our sort of target unitary U, or essentially the computation, is generated by Hamiltonians H0 and Hj. The control functions of interest that we want to learn are these functions Uj. And as you see, our generators are in P. So the goal is to reach a target computation in a minimal time, subject to certain control constraints. The induced length on GK leads to a sub-Riemannian geodesic. These are all points that I actually show in my thesis. So we showed fundamentally in my thesis that there is an analytic way to deduce the optimal control pulses for certain classes of quantum control problem situated in symmetric spaces. Effectively, we fix an element in the Cartan subalgebra and fix a direction, and then the geodesics can effectively be traced out using the generators in P. This will make sense in the next slide. So, for example, say you want to perform a Z rotation, but you can only perform X and Y rotations. You can't do this. You effectively just have to apply, X and Y rotations, and because of the way that they commute, you can actually generate a Z rotation simply by performing X and Y rotations, and the angle, the kind of length of the length of the sub-Riemannian geodesic here is fundamentally contingent on the angle of from the pole that your sort of target target is at. So and that angle is theta. So as long as theta is constant, then fundamentally we show in our earlier work how you can find these time optimal solutions. Um, so again, we have our sort of target in G. We have our Cartan commutation relations. It means that our quantum computation can be decomposed in the KAK form. This is important for our method because it's effectively what we do is we write down our target computation, U, in terms of a KAK form, which is here. And then this second equation here is actually Schrodinger's equation again. Uh, uh, it's just written down in a particular way, but fundamentally what it shows is certain elements belong to both the symmetric or the antisymmetric subalgebra. And so what we show in our earlier work is that fundamentally, if we restrict generators to P, we can generate what we have what's called a minimal connection. The long and the short of it is that fundamentally we can cancel a number of terms in this wider equation so that it leaves only the antisymmetric motion along the symmetric space. It makes the problem simpler to solve analytically. And the action of K can be thought of here as a gauge. So I'm going to skip through a lot of the mathematics actually, just in the interest of time. I would draw your attention to our papers and my thesis for more detail, just because I want to sort of get to the main sort of point here. So again, the sort of key point of our result, which we then imported into quantum neural networks, is that for certain classes of problem, you can analytically deduce what, given the energy of the system, omega, what the optimal time t, capital T, should be. And that fundamentally then allows you, together with the other techniques, to write down the Hamiltonian, which is what we have here, HT, which is time optimal, which is a time optimal quantum circuit to perform the quantum computation of interest, which is also a sub-Riemannian geodesic. So I'm just going to skip through again. Apologies, just in the interest of time here. The key point for our method is it reproduces the results from known time optimal quantum control problems, but in a much simpler analytic way. And that's why we have confidence in the method. Okay, so the paper I'm actually presenting here at this conference is really about then taking that result, which I had to spend a bit of time talking about, and converting into quantum neural networks. Why would you do this? Well, because you may quantum computing is complex. You may have incredibly computationally intensive requirements to perform computations or to try to solve them and solve the control problem per se. And so you may want to build a neural network to solve or to essentially perform some of the analytic and numerical calculations that are needed to obtain the sequence of control pulses you need to apply in order to generate a time optimal quantum control um, computation. So effectively, how do we do this? Well, we say, well, one way is you could just throw a transformer network at the problem and then hope it comes up with a series of control pulses that respect symmetries that you need to respect that are time optimal. The chances of that happening are, well, probably not that great because we know there are challenges with transformer models, and other types of ML models. So instead, we turn to models where what we call gray box models, where we essentially integrate symmetry properties that we want and know must be respected by the neural network and by the system into the neural network itself. And this is what's called an equivariant quantum neural network. The sort of core idea is that the network respects symmetry groups or symmetry properties, symmetry transformations, so that you can be confident that both the network and the output is respecting those symmetries. Why does that matter? Because quantum computing must preserve unitary symmetry, for example. But also for quantum control problems with symmetric space targets, you want the symmetries that allow you to do the decomposition to be preserved, because that's what allows you to sort of, essentially apply these techniques to obtain the time optimal circuit. If you don't apply those symmetry techniques, it's largely intractable. So the kind of reason we do this is because we want to apply and enforce the symmetry properties to make the problem simpler, so we can find the time optimal quantum computation. And again, invariance and equivariance are slightly different. Again, I've sort of uh, draw people's attention to the literature in the paper on this. But again, the sort of key point here is that we have integrated our techniques, which I very briefly skimmed over, into a quantum neural network setting. And I'm leaving what a quantum neural network is actually understood. Appreciate many people won't have a background in that, but again, it's in the paper and in the references. And yeah, apologies, I'm skipping through here just in the interest of time. I've got about 5 minutes left, but there's sort of, uh, so I'm just going to skip to actually how we built the network and what we did. What we did was we built the network using these symmetry properties, and then, uh, uh, in a way which was different from what we did initially with the analytic solution, and asked the network to learn the gaps, learn certain elements or certain numerical elements in the problem that can't be learned from the symmetry transformations. And fundamentally, but still, while still preserving the symmetry properties of the system. And fundamentally, we found that it could and did. And I should say, this is a classical simulation of a quantum neural network. We don't yet have scalable fault-tolerant quantum computers. So how do you impose symmetry? Well, you impose it in the layers of the network. So the layers of a neural network are just the composition of functions. You can construct them in a particular way to respect symmetries. And what you want is, as the data is moving through the network, through what's called the residual stream of the network, you want the symmetries to be reflected at each stage. Each layer is a computation, is an algorithm. You want that algorithm to be respecting these symmetries, so that the symmetries are fundamentally respected in the final layer, which is the output. How do we do this? We did this, so, okay, that probably maybe makes sense to people, but of course, how you engineer this is problematic, because on the one hand, you want the neural network to have the versatility to explore the solution space, to not be too constrained, otherwise what's the point of it? But if it's not constrained enough, then it won't respect the symmetry property. So you sort of have this sort of trade-off there between respecting the symmetry properties enough to maintain the structure you need, but allowing the versatility for the network to, essentially explore and use its optimization architecture to find the thing that you cannot analytically find. To solve this, we essentially combined what we called alternating KP blocks. So I'll just skip to a sort of picture here. And we also imposed in the loss function of the network, I should say, three requirements. The first is what you always do with a neural network, which is seeking to perform learn a quantum computation. You want the fidelity of the target computation to match the estimate. Secondly, we wanted an equivariance penalty, so the network would penalize updates to its weights, which cause variation from the equivariance principle, and there's a regularization term. So I'll just skip to the picture. Okay, here we go. Yeah, so what we fundamentally were doing was to sort of balance this sort of explore exploit sort of trade-off. We had certain layers that had operators from K and then certain operators from P or A. And so fundamentally what that allowed us to do is it enforces symmetry while enabling the dynamics. I appreciate I'm not sort of explaining this in full detail because I've only got a couple of minutes, but fundamentally the kind of key takeaway here is that we were able to integrate these novel symmetry techniques into the neural network, but we did it through this alternating layer-wise approach that ultimately allowed us to, or sorry, allowed the network to explore these solutions while preserving the symmetries. I've only got about a minute left, so very much apologies for having to skip through. But fundamentally, one point of interest is that the techniques that we developed have a lot of relationship to lambda problems. So what we sort of showed somewhat is that they are related to the types of energy gaps that you see in lambda systems. All right, I'm just going to skip through to the sort of, this is a proof of concept paper. There's a lot of issues around noise and decoherence that need to be explored. And but fundamentally, I believe the kind of key takeaway is that this paper shows how we can take geometric control techniques, symmetry techniques, embed them in quantum neural networks, and use them to help solve optimization problems in quantum computing. And that is my talk. Please reach out if you have any questions.